James Webb Space Telescope have components attached to the back of each of them. What exactly are these and what do they do? Well, we're here at Ball Aerospace in Boulder, Colorado to find out. So Brad, what's going on over here now?
Well, we are bonding items to the back of the mirror, and that is to distribute the loads during launch as well as to distribute the loads during the mission.
And this is a precursor to more items being attached to the mirror, right?
Yeah, that's correct. The next step is when we attach the hexapod assembly and the radius of curvature subsystem onto the back of the mirror.
Sounds like a mouthful. I think it'd be better understood if we actually see one.
Sure. The hexapod assembly has the 6 rigid body actuators. Its job is to manipulate the mirror in 6 degrees of motion. The radius of curvature subsystem, it's one of the 6 struts, and there's an actuator that goes to the center of the mirror. It can very precisely change the radius of curvature of the primary mirror. Because the mirror consists of 18 primary mirror segment assemblies, those 18 primary mirror segment assemblies must be adjusted while on orbit to mimic a perfect primary mirror.
So Brad, can we take a closer look at these actuators?
Talk to Jake Lewis, and he will bring you up to speed with the actuators.
Jake?
Yes.
Yeah, Brad told me that you are the man with the actuators.
Absolutely.
Can we take a closer look at them?
Sure. So here we have the hexapod, and we're aligning the actuators onto it. A precision alignment fixture allows us to build each hexapod identically. Now that they've positioned the actuators on here, they've got to verify that it's in tolerance. So they're measuring it to make sure that it's in the exact position that it needs to be.
Do you have different actuators for the different mirrors, or are they all the same?
No, one of the things that we've done is that all of the mirrors have exactly the same actuators on them.
Secondary, tertiary, all those?
Just the secondary and primary mirrors have actuators. The tertiary doesn't have any actuators on it. It stays fixed. But the only difference between the primary and secondary mirror hexapods is the size of the frame. The actuator assembly all remains identical, and that's a cost savings and a great simplification for us.
Well, thanks for giving us a sense of what actuators are on the James Webb Space Telescope and the hexapod assembly.
You're welcome.
As you can see, these actuators with the hexapod assembly make these mirrors on the James Webb Space Telescope much more complex than the ones that, say, you might have in your bathroom. But these mirrors have a job to do, to look at a universe billions of light years away. To consider when you're designing mirrors for a space telescope. They need to be lightweight, sturdy, and not change shape so much just because it's a little cold, like 400 degrees below zero. Glass won't do the trick like it does here on Earth, but beryllium will. So where do you find this rare metal? The West Desert of Utah, of course. Hey, so Rob, where are we going?
We're headed to our current active open pit beryllium mine. This mine is the only mine like this in the entire world. So these are the only beryllium miners that you'll find. We are currently standing on the edge of our active pit, where the hard rock is being excavated that covers the beryllium ore.
So why is beryllium so valuable?
It is very strong and very light. It's 1/3 the weight of aluminum and has 6 times the stiffness of steel.
How tough is it to find beryllium?
It took us about 30 years to gather all the data and information to design and develop this mine.
And once the ore leaves this mine, is it ready for the folks at the James Webb Space Telescope program to use it to build the mirrors?
No, after the ore material leaves the mine, it is shipped to the processing plant about 50 miles east of here.
Oh, great. Well, thank you so much for welcoming us and letting us see your beryllium mine.
You're very welcome.
So, Phil, we just came from the beryllium mine, and Rob told us that you guys take the ore that they over there dig up.
Yes, that's right. The ore is hauled in and put up in these pockets here, and then we crush that ore and mix it with water to start the process.
All right, so Phil, we just came from the ore, and you said they crush it, and then what?
Well, this is the ore, what we get from the mine, and then we crush it to a very fine slurry, and then after we leach it, we have the beryllium in the water, and the bottom has most of the beryllium leached out of it. What's happening here is that the slurry from the leaching area is brought out here through a pipeline, and it goes into this well where it's mixed with a flocculant.
What's a flocculant?
It ties up the fine particles with the big particles so they will settle to the bottom.
Okay.
And then the clear overflow becomes the solution that we process to get the beryllium out of. This is a solution that we just came from those big tanks out there, and that'll be filtered to remove those fine particles. And then we mix that solution with the organic layer, and the beryllium goes into the organic layer, and most of the impurities stay in the water layer.
Now you said organic layer. What does that mean to the rest of us?
It's like oil and vinegar. This is the oil in your oil and vinegar.
So you're putting oil in, or you're putting vinegar in?
Yes.
Both.
Both.
Okay.
The vinegar would be the water solution, and we have a special extractant in the oil layer.
Okay.
So it flows to the top, and we can concentrate and purify the beryllium.
It's still a liquid here. What then happens?
We purify it and precipitate it into a powder, which we then package.
Beryllium dust is not exactly the best thing to be near, but can we see something that resembles a powder?
Yes, I have some sodium carbonate right here, which is very similar to the texture and the fluffiness of our powder if it was dry.
It looks kind of like a talcum powder, really.
But very much so.
Okay.
These are the drums that we have our material in, ready for shipment.
And you said shipment. Where are they going to go to next?
These will probably go to Elmore, Ohio.
Elmore, Ohio has what?
Elmore, Ohio is the plant Brusher Elman owns that converts it into finished goods.
So it's going to come out looking like a metal.
Yes, it'll come out as a metal, an alloy, or an oxide.
Well, thanks so much for showing us your plant.
You're certainly welcome.
While you can find beryllium mixed with metals in everyday life, like computers, cell phones, and even your car, you can only find pure beryllium in specialized items like X-ray machines, space satellites, and now the James Webb Space Telescope. One of the reasons the James Webb Space Telescope will usher in a new era of astronomy is its unique set of mirrors. To perform at their very best, these mirrors need to be shaped with exact precision. To find out just how that gets done, we're here at L3 IOS Tinsley in Richmond, California. So Ed, what's going on here?
Well, we're shaping the mirror using several different processes to take it down to about 20 nanometers of surface error, which is about 1/5 the diameter of a human hair.
What else are you trying to get rid of?
We have to remove fine scratches down to about 0.008 of an inch. Anything wider than that, and it starts to reflect light and diffuse it, so you don't get a good image off the telescope. We're removing the grinding compound. Actually, it's a rough polish compound, and beryllium that's actually on the surface of the mirror, and we have to clean it before we go on to the next process. He's removing it off of the part using a solvent.
The solvent he's using, is it just Windex or much more?
No, we can't use Windex. It has chemicals in it that will actually attack the surface of the beryllium and cause it to corrode. So we have to use a isopropyl alcohol in order to clean the part and acetone it.
Robert, Ed showed us the cleaning of the mirrors. So what's going on here?
After rough polishing, we have to get rid of the texture that's left on the surface. The smoothing process will plane over that texture and give us a true mirror surface.
Could you do this by hand?
People used to do this by hand, but you could not make these mirrors. It'd be very difficult to not have residual texture in these mirrors.
It looks like water. Is it water?
No, it's not water. It has a fine abrasive particle in it and some other chemistries that we know work well with beryllium. Beryllium's a very difficult metal to polish.
So Robert, it kind of reminds me of what women try to do, exfoliate their skin, trying to get rid of that top layer of skin cells to show a brighter layer underneath.
Well, the mirror surface, when it comes to this process, has a texturing on it. And so this process will take the little peaks, saw it off, until finally you have this perfect plane. And these are not flat mirrors, but you want that surface to be just very continuous. If it has roughness in it, it won't perform well because each little lump and bump on the surface then reflects light in a different direction, and so it doesn't come back to the detectors. So this process helps it to be extremely uniform, so you have the maximum amount of surface area returning the light for you.
Well, thanks a lot for showing us this.
Thank you.
So these processes the mirrors go through, like the rough polishing and the smoothing, are done over and over again to make sure the mirrors on the James Webb Space Telescope have a smooth surface and the correct shape. The 18 segments making up the primary mirror on the James Webb Space Telescope will be held in place by something called a backplane. Since each hexagonal mirror is about 3 feet tall, you can imagine this backplane is really huge and very complicated to make. To find out more about how this is being assembled, we're here at ATK in Magna, Utah, and we're happy to have with us Bob Hellickson. He's the project manager for the James Webb Space Telescope. Thanks for having us over.
Thank you for coming to visit us, Mary.
First of all, how tough a job is it to make a backplane for the James Webb Space Telescope?
Well, what we're standing in front of right here is 3 of the full-scale hexes for the backplane, and this was manufactured out of wood that established both the tooling approach and the assembly approach that we'll use for the flight article.
Now, you didn't just go from this to the real thing, did you?
No, we did not, as a matter of fact. This structure was the first, made out of wood. Then this same size, 3 hexes, was made out of the graphite composite material. It was taken down to the 30 Kelvin level, or minus 405 degrees Fahrenheit, and it was measured for its performance on stability, meaning it had to stay very stable through that entire temperature regime.
So, Bob, I understand the real backplane is here at ATK now.
Oh, absolutely. We can show you that, and we'll have to go in the clean room next. I want to show you some electronic measuring equipment to make sure that everything meets its final dimensional performance before we deliver.
So is it like a GPS where it detects where that ball is located at any given time?
Yeah, that's exactly right. That ball coordinates back on its surface to where the model is for the corresponding feature.
This is very interesting stuff, but the suspense is killing me. Can we go see the backplane now?
Absolutely. Let's step around this side and we'll show you the rest of it.
Great.
This is the center section of the backplane, and it will house 12 of the primary mirror segments.
You said center section. It's not the whole thing?
Correct. The full-size mirror will have 18 segments, and what's missing here that'll come later are 2 wings, each holding 3 segments or 3 mirrors.
And why break it out into a center and 2 wings?
The launch vehicles don't have the dimensions to accept the entire width, so it has to fold up, and that's another unique feature here is we're deploying 3 of the hexes on each side or both wings.
This is not exactly a flat structure. It looks like it's got a little bit of a curve.
That's correct. The backplane matches the parabolic shape that they want the primary mirror to end up with.
Besides holding the mirrors in place once James Webb is in operation, what else is the backplane for?
The backplane also provides stability to the entire observatory. So what's missing here, you'll see later, is a backplane stability frame that reaches up about 8 feet off of this section. It will house the instruments for the observatory and provides a lot of the strength for the launch.
Well, thanks for showing us ATK's backplane.
Well, thank you very much for coming to visit us, Mary.
So as you can see, this backplane will be ultimately thermally and structurally stable, important for the 18-segment primary mirror to stay still so that the James Webb Space Telescope can take its wonderful images of the universe.